In this video, we'll be discussing some more of the general theory of linear differential equations with the aim of developing a general approach to solving these kinds of equations. So just to remind you, a linear differential equation is any differential equation of this form here, where the ai, the coefficient functions, as well as the g of x, are all continuous over the same interval, and the leading coefficient function here is not equal to 0. Okay, so given such a linear differential equation, this existence and uniqueness theorem just says that there is a unique solution subject to these initial values here. So that's to say every initial value problem involving a linear differential equation has a unique solution. And these initial values, by the way, all they do is they specify y and its derivatives at a single point, x0. All right. So that's the existence and uniqueness theorem for linear differential equations. This theorem has a number of important consequences, which we'll get into. But before doing so, let us just recall the following definitions. So a linear differential equation is just called homogeneous when the right-hand side is equal to 0. And then for homogeneous equations, we have the following theorem, which is called the superposition principle. And that just says that any linear combination of solutions to a homogeneous differential equation is itself a solution to the same homogeneous linear differential equation. So just more exactly, given any solutions y1 up to yn to a homogeneous differential linear differential equation, this function is itself going to be a solution where the c1 and the cn are arbitrary here. Okay, another concept involving linear combinations is that of linear independence. So a sequence of functions is called linearly independent if this implication holds here. And what this implication is saying is that the only linear combination of these functions which adds to 0 is the trivial linear combination. So if you find a linear combination which adds to 0, the only way that that could have happened is that the constants themselves were in fact 0. So this concept of linear independence actually is a concept in linear algebra for vector spaces. And in 2 dimensions, it really just captures the meaning in a formal way, what it means for 2 vectors to point in different directions. So in this picture here, this x here and this y here are point in different directions. And so we say that as vectors, they're linearly independent. Linear dependence, the opposite concept, is when they're not linearly independent. And that just means that one vector is the scalar multiple of the other. So in this case, y and z are not linearly independent, so they're linearly dependent. All right, so in a sense, for functions, we can say that y1 up to yn point in different directions, so to speak, when they're linearly independent. Okay, now with this concept of linear independence, we have the so-called Wronskian. And in general, if we had to try and verify when a given sequence of functions is linearly independent, we have to really verify this implication here. So that's to say, making this assumption, there's a sequence of logical steps ending with this conclusion. Maybe we can just illustrate this. So for instance, if we take the sequence of functions y1 equal to sine x and y2 here equal to cos x, then the claim is that this is linearly independent. But to show that these are in fact linearly independent, what we have to do is suppose we have to make the assumption that this linear combination, any linear combination here, which adds to 0, makes these constants c1 and c2 0. Okay, so now after making this assumption, we can only use logical steps which are valid. So from here, we just replace y1 by what it is. And from here, we just understand that this statement here is really making a statement for all x. So for any x, if I plug it into this equation here, the resulting equation should hold. So in particular, if I substitute x equal to 0, well, let's say x equal to pi over 2, then here I'm going to get this. And now this equation, since it must hold, immediately gives me that C1 here is equal to 0. Because why? Because the sine here is 1, and this here, the cos here, is going to be 0. Okay, now we could have also have substituted a different value for x. We could have substituted, for instance, x equal to 0, and here we would have gotten sine of 0 plus c2 cos of 0 equals 0, and this will then also imply that c2 is equal to 0. So what we've just done, what this argument shows, is that if I make this assumption here, then I can use purely logically valid steps here, here, and here, and these in turn make this conclusion here. And so for that reason, this implication here holds, and that then just validates that these are in fact linearly independent functions. Okay, so that's a bit of a technical thing to do every single time, but this begs the question if there's a simpler way can we for determining whether a sequence of functions is linearly independent. And luckily there is, and this involves what's called the Wronskian. So given a sequence of functions, y1 up to yn, we can compute the Wronskian, which is another function of x. If y1 up to yn are functions of x, then so is the Wronskian. And the way you compute the Wronskian is you put the sequence in the first row, and then you produce the other rows just by differentiating. So in the second row, first column, you have this term, which is first derivative. And here you would have just below that you would have the second derivative of y1. And at the end, you want to get a square matrix. So you take the n minus 1th derivative. So this gives you the so-called Wronskian, or this gives you a matrix, and the determinant of that matrix gives you the so-called Wronskian. And with respect to this Wronskian, we have the following theorem. And that theorem is just that the functions yn up to yn are linearly independent if there is a single point for which the Wronskian is non-zero. So just to see how this would apply to our earlier example, if we took the Wronskian here of our two functions sine x and cos x, as we did earlier, we already proved that these are linearly independent, but let's see it from a different point of view. Here, we would take the Wronskian, so we take sine of x, cos of x. Here we get cos of x and negative sine of x. The determinant here just will be, you get it by cross-multiplying here. And this will just give us negative sine squared minus cos squared, so we just get negative 1. And of course, that means that the Wronskian at any point is actually non-zero. And so, in particular, these two functions are linearly independent. Okay. Now, in fact, when our functions, like the previous example actually, are solutions to an nth order linear homogeneous equation, so if this sequence here, the y1 up to yn, are solutions to an nth order linear homogeneous differential equation over the given interval, I, then it will happen that if we can find one point where the Wronskian is non-zero, then in fact the Wronskian is non-zero for every point in the interval. So that we have so that this theorem is really just saying that the functions y1 up to yn are linearly independent if and only if the Wronskian is non-zero for every x in our interval. And just to explain the reason for that, we can just take a look at this system of linear equations, just to remind you a little bit from linear algebra. So any system of linear equations, as is given here, can be fully captured by a single equation involving matrices. And in this case, if we call this matrix here A, and this one B, and this one C, then this is just saying that the multiplication of two matrices is equal to another one. Now, of course, we're interested in being able to solve these kinds of equations, and one of the main results of linear algebra is just saying that this equation here, ax equal to c, has a unique solution, which in this case will just be b, but it has a unique solution So just to remind you, the thing that we're solving for here would be the x, right? So this equation has a unique solution if and only if the determinant of A is not equal to 0. Another way to say this is that the only solution to the equation AX equal to 0 has only the trivial solution. Okay. So this just gives you 3 characterizations of when you can find a unique solution to your linear system, and this approach will be very useful to us, so we'll keep it in the back of our minds. So the first thing we want to do is just try and understand why this corollary is in fact true. So let's just see what is known here. The claim is that the functions, the y1 up to yn, which are solutions to an nth order linear homogeneous equation, these are linearly independent if and only if the Wronskian is non-zero for every number in our interval, for every x0 in I. Now we already know that if the Wronskian is non-zero for just the one value, then the functions are linearly independent. So we actually already have half by this theorem up here. So the real question is, why does a sequence of linearly independent solutions to an nth order linear homogeneous equation, why does this give us that the Wronskian is non-zero for every x0? So to see this, let's consider the following. First, we're going to, of course, we're supposing 2 things here. We're supposing the first thing is that the y1 up to yn are solutions to an nth order linear homogeneous equation. And secondly, we also are making another assumption. We need to show that for every x0, the Wronskian is non-zero. So we need to just let x0 be any number. Okay, so let's try. So we're given this data, okay, x0, and we've given that this is linearly independent. Now we want to try and solve the following system. So we want to try and solve the system given by actually this part of the equation. So here we have a linear system. And what are the unknowns here? The unknowns are the C0. We are given the functions y1 up to yn, and we're given this point x0. So these here are known numbers. And so in fact, we're just looking for the C1 up to Cn. That's the first thing we're going to do here. So now given that, we can actually rewrite this system here as this equation here. That's what this is. So here we have a specific matrix. We have this matrix here. Let's call it W times C equal to 0. And we're solving for C here. Okay. And C, of course, can be anything. So we're trying to analyze the system W times C equal to 0. Okay? And the thing to see here is that if we have to define our well, firstly, just to make an immediate conclusion, this thing has the only trivial solution. If and only if the determinant here is non-zero. And remember, the determinant of this is exactly the Wronskian at the point x0. Okay, so how can we get that this system here has only the trivial solution? Well, that's going to go back to this existence uniqueness theorem. If we define our function y here to be this linear combination, then what do we know? We know then that firstly the y here is a solution to the dE. By the way, we probably should have labeled this dE. Let's call it star. So y, because it's a linear combination of solutions to a homogeneous equation, so is this, then it must be a solution to the same equation. But moreover, these numbers here specify initial values. So we have here a specification of initial values, and they must all be equal to 0. Now there is actually always a function which has this property, and it's the 0 function. Setting y equal to, let's say, theta equal to 0, this would be a solution to any homogeneous equation, and moreover it would have these initial values. So that has a very important consequence by the existence and uniqueness, because we know that for an initial value problem there's only one solution. So this means that the whole function y, that this function here, has to be the 0 function. Okay? So we just to say that again here, since y is a solution to our differential equation with y of x0 equal to 0, and this continues all the way up to y to the n minus 1 of x0 equal to 0, we must have that y is equal to 0. So we have by existence and uniqueness theorem so I'll just underline that here, that y is equal to 0. Okay? So that just means that since y is just equal to c1 y1 all the way up to cn yn, this is equal to 0. And because we have assumed something, the y1 and the yn are linearly independent, we immediately get that the c1 is equal to the c2 is equal to all the way up to cn is equal to 0. Which is to say that this linear system this linear system here has only the trivial solution. And that is exactly the same thing as saying the determinant is non-zero. And that is exactly the same thing as saying the Wronskian. So the Wronskian is non-zero. Okay. And by the way, let's just recapture this theorem here one more time. So assuming that y1 up to yn are solutions to an nth order linear homogeneous differential equation, and assuming that x0 is any number in the interval whatsoever, where we're considering the differential equation, we get that the Wronskian is non-zero, always. Okay. All right. Now, along similar lines, we can actually produce something, some other kinds of conclusions from this existence and uniqueness, and so we'll get into that now. One of the main concepts in the theory of linear differential equations is that of a fundamental set. This is also a concept actually in universal algebra, linear algebra, which is the concept of a basis. So the basis for a vector space. But in any case, so we say that the functions y1 up to yn, so these solutions to a homogeneous linear differential equation of the nth order, they are called a fundamental set if every solution, y, is just a linear combination of those functions. So in our two-dimensional space analogy, the concept of a basis really just captures that any point can be made up from these two vectors. So for instance, if we have I and j, the normal unit vectors, then we know, of course, that any point is just equal to some linear combination of these. Okay? Now, one of the main, an obvious thing really is that actually, if I take any two vectors which are pointing in different directions, then in fact they'll have the same property, that the point here can be formed by some linear combination of let's call these, let's say, a and b, or v and u. There will be some numbers, s and t, let's say, such that p is equal to s times v plus t times u. So what that is just saying is that any two vectors which point in different directions will span the whole space. So a very similar thing is happening here. If y1 up to yn are solutions to a homogeneous linear differential equation of the nth order, then they're called a fundamental set if every solution can be formed as a linear combination. And then we have the following theorem, which just says that any n linearly independent solutions to a homogeneous linear differential equation of order n forms a fundamental set, which is a really remarkable fact, but it has a very easy to understand explanation, which I just want to quickly end this video with. So suppose we're given any solution and we're given a fundamental set. Let's try and show that that we can write that solution, this one here, as a linear combination. Okay, so let's say that we're given y, a solution to this linear differential equation, and let's set, let's define z0 to equal y at x0 and zn to equal y at xn. Hi everyone, sorry I was interrupted, but we'll continue here. So the thing that we wanted to prove is to show that if we are given any n linearly independent solutions to a homogeneous linear differential equation, then in fact they form a fundamental set. So this is kind of analogous to saying that if I give you any two vectors in R2 that point in different directions that are linearly independent, then in fact they are a fundamental set, which is to say any point can be formed by some linear combination of these vectors. Okay, so that's the main concept here that we want to kind of justify. So we'll get into that. So in order to prove that, we need to suppose that y is any solution to a homogeneous linear differential equation, which is what we're doing here. And we then take any point, x0, in our interval, and we let z0 be equal to y of x0 and zn minus 1 equal to y to the n minus 1 of x minus x0. And we want to consider a linear system, which is this one here. Okay, now why are we considering this linear system? Because we can solve it. So this linear system becomes this equation for matrices. And so just thinking about it more equationally again, this is W times C is equal to Z. And the important thing to see here is that the determinant here of W is in fact just equal to the Wronskian at the point x0. And by what we've just shown earlier, this is not 0. So that means that this system has a unique solution, and so there is a solution, and in fact it's unique. Great. So that means there are C1 and Cn solving the system, and that's just to say that if we define this function theta in this way, so remember how we've solved this, very important to see this. Remember how we've solved the linear system above here. The linear system is such, if I multiply this matrix, let's just see what we get by the first row. So we multiply this here by this, we're going to get y1 of x0 times c1 plus all the way up to c n times yn of x0. So that must be z0. And of course, this happens similarly for every row. Ci y to the power of I 1 of x0 equals zi. Sorry, c1 times y1 yn of x0. And okay, the point of doing this is that if we define, we've solved the system such that if we define our theta to be this, then we have a very important fact, and namely that theta, because it's a superposition of solutions to our homogeneous equation, it's a solution. It's a solution to our homogeneous differential equation. And moreover, it's a solution which has the same initial values as our function y. Remember, these z's were defined as the initial values of y at the point x0. And so, by the uniqueness, by the existence and uniqueness theorem, y is equal to theta, and so that y is just a linear combination of the solutions in our fundamental set. Okay, so we can just wrap this video up by discussing in general how one would solve a linear differential equation. So here is how we solve a linear differential equation. First, we need to find the fundamental set for our the associated homogeneous equation. So given any linear differential equation like this, we consider the homogeneous equation that's associated to it, just to set the right-hand side equal to 0. Then, because this is a homogeneous equation, we look for a fundamental set to it. So we find a fundamental set to this associated homogeneous equation. Then step 2 is we find a particular solution to the equation. So a particular function that when I substitute it into the differential equation, it holds. And then the final solution to this differential equation, that is to say, every solution to our linear differential equation will be of this form here. Y is equal to some homogeneous component, which is given by this, plus the particular solution. Okay, so that's it for this video. Thank you.